Hello, my name is Brintey Lewis, and for my lab I recorded my friend rolling a Campbell's chicken noodle soup can across my kitchen counter. Today I will demonstrate how using tracker software and vIdle, I was able to analyze the position of the displacement of the can at individual time frames. From this data, I was able to demonstrate relationships of position, velocity, and net force using Newton's second law of motion. In physics, we can use two formula relationships to predict the displacement of an object and the change in velocity of an object over time. We measure velocity as a change in displacement over time. So for a specific time period, we can predict the velocity of an object if we know its initial and final position. Given the initial velocity of an object, we can also predict the change in velocity over time using Newton's second law. From Newton's second law, we can conclude that if the net force of an object is zero, then the velocity of the object should not change over a given time frame. Thus, for a moving object, we should see constant velocity unless a non-zero net force is acting on that object. For this experiment, I uploaded a video of the rolling soup can to tracker software. I then defined my axis on the video frames in order to measure change in displacement. The coordinate frame used in this video supports a right-handed axis in which the soup can travel in the positive x direction. Had I oriented the axis so that the x-axis was flipped, I would see the soup can traveling in the negative x direction. Regardless to the change in axis orientation in the y component of the object's velocity, the y component of the object's velocity does not change, because only the displacement that is occurring is along the x-axis. Before recording any data points on the axis, I also had to define the length of the soup can using a calibration stick to obtain a relative measurement of space. Using Tracker, I recorded the displacement of the can over 18 time intervals, each 0.1 second in length. In Tracker, my experimental position versus time graph produced a line with relatively constant slope. If I was to measure the displacement between each time interval, I would be able to measure the velocity of the soup can at each instantaneous point. The slope between the instantaneous points shows the velocity of the soup can for that time interval. Because my position versus time graph shows relative constant velocity, we can assume that the relative net force on the object is zero. Because we assume the net force on the object is zero, we can also use Newton's second law to make predictions about future velocities. In an ideal experiment, the velocity between each time interval would show to be equal. On a position versus time graph, this would be supported by a straight line with constant slope, in which the instantaneous velocity of the object was constant through the video. We can also use vIdle coding software to show a comparison of a computational prediction using Newton's second law and the actual experiment. Here we must first define the formula we'll be using to make these predictions and the initial parameters. In my computational prediction, I first wrote a code to build a window in which I will model Newton's second law. The next part of my code shows the initial parameter for the position, velocity, and time. The final part of the code is a while loop that will serve as the updating function for the final position and the final velocity of the rolling can through each time frame. When I ran the program, the model produced showed a variance of an ideal model, and by comparing my computational model predictions to my observed model, this experiment shows that our soup can did not exactly follow Newton's second law. This could be due to small frictional forces or other outside forces creating a non-zero net force on the can, slight variance in axis definition, and human error in measuring displacement.